In this video, we are going to talk about some important topics on topological spaces from its very basics. Okay, first let me remind you what a topological space is. Let us take a non-empty set X and a family of subsets of X, not necessarily family of all subsets of X. Okay, but the family T must follow these following conditions. The first condition is phi and x, both being subsets of x, has to belong to this family T. The second condition is arbitrary union of any members of the family T has to belong to T. Similarly, the third condition is finite intersection of any members of T must belong to T. That is, let X be a set and S1, S2, S3 be subsets of X such that T is a family of subsets containing all S1, S2, S3, etc. Now, we can say that any union from where alpha belong to any infinite or finite set lambda, S alpha must belong to T, as well as intersection alpha belongs to some finite set, call it lambda naught, S alpha belongs to T. But if this lambda naught becomes an infinite set, then this intersection may or may not belong to the set T. Okay. Now we will take some examples of topologies. First one is indiscrete topology. Let X be any non-empty subset and T be a family containing only two elements, which are phi and X. Then this topology, this ordered pair XT, forms a topology called indiscrete topology. For discrete topology, let us take any non-empty subset X not equal to phi. Then we know that a power set contains all subsets of X, including phi and X itself. If we name this power set as T, okay, then this ordered pair XT forms a topology which is called discrete topology. This is indiscrete topology containing only two elements, phi and X. It can also be called as trivial topology. And this one is discrete topology. That means it contains all subsets of X. So all subsets of X is an open set. Why? Because the elements of T in any topological space, forms a complete list of open sets. So every set of X in this topology is an open set. The next is standard topology. For standard topology, we take X is equal to R, the real number set, and T as this type of subsets A, B, open set A, B, where A, B are all real and A lesser than B. Okay, A, B are all real. So when T contains this type of subsets, X, the ordered pair XT is called standard topology. What about cofinite topology? Now this one is very much important example, cofinite topology. For this topology, we can take X is equal to R or X is equal to some closed interval AB or some open interval AB whatsoever. In this case, I am taking x is equal to r and t is equal to some set S where S is a subset of X and complement of S in X is finite. This will form, now this ordered pair xt will form a topology which is called cofinite topology. So in this case, an open set will look like what? You can see this is an open set. R minus some finite number of elements, A1, A2, AN. This. So complement of this set will be only this set. Complement of this whole set will be this set, this finite set. So this whole set must belong to T. So this set is an open set. So this is a very much important thing for cofinite topology, which says this is an open set in xt. Okay, you have to remember that. And the next is lower limit topology. For standard topology, we have taken such type of intervals. For lower limit topology, x is same as r, but t will be this type of intervals. Less than b and ab both are real. Same there can exist upper limit topology, for which we will take a, b, this type of intervals, semi-open intervals. Now these are all important examples that you can easily check by yourself why this forms topology. Okay, now let's come to our next topic, which is base of a topology. Base of a topology can be defined several ways, but let me define you like if xt be a topological space, then a family B, which is a subset of T, follows the conditions that any member of T can be written as union of elements of B. Union of elements of B. Okay. B alpha is to B. Or in other ways, we can say that B is such a set that members of B generates union of members of B generates elements of T. Okay, so any element can be written, call it T1. T1 is an element of T. So any element of T can be written as union of members of B. Okay. So this is called the base of a topology topology xt. Let us take some examples. Consider the topology x tau, where tau is the discrete topology, that means the power set of x. Then what is the basis? What is the base of T? Let base be A, B, and singleton, and base is contained of every singleton where A, B, etc. all elements lie in X. So this is a base for this topology, but this does not form a topology by itself. A topology T is the elements that is generated by union of members of this base B. Okay, now let us take another example. This is for finite case. Let T be phi singleton A, singleton B, and since A and B both singletons are in T, the set containing AB also lies in T because this is union. Okay, now a basis for T will be a base of T will be A, B, okay, and phi. We can call B a base. Why? Because any element of T can be generated by unions of these elements. Okay? Oh, this also contains X itself because there is an element X in T. So there must be an element X in B so that we can generate X in T. Okay. And always remember that phi always belongs to the set B. Now let us discuss a very much important topic which is called stronger topology or weaker topology. Well, if I take a set S containing 3 elements A, B and C and T1 be a topology defined on X such that T1 is equal to phi singleton A and X. This forms a topology, right? And so does T2. This also forms a topology. But T2 has more elements than T1. And also T2 does not have only more elements than T1. T2 also contains T1. In this case, T2 is a stronger topology than T1. Now, if I define stronger topologies or weaker topologies in view of bases, then it will become a little different. Okay, see here T1 contains phi, A and X. This is T1. T1 contains A and X, and phi is a null set, so I cannot draw it right here. And T2 contains A, B, AB and X as well as phi. Okay, so what you can see that T2 contains more element, plus if we consider base of T2, it will become phi A, singleton A, singleton B and X. But if we consider base of, well, I write base of T2, and if I write base of T1 as B of T1, it is phi A and X. That is T1 itself, right? So for every element B of T2, for every element from B of T2, there must be an element, let us call B2 be a basis of T2, and B1 be a base of T1. We will call T1 as a stronger topology than T2 if for every element B belonging to B2, T1 is stronger. Okay, we will call T1 stronger. If for every element in B2 there must exist a call it B dashed in B1 such that B dashed is contained in B. Okay, so then we will call T1 as a stronger one. For stronger one, then let me explain you by some other example. You can see, let us consider this slab as a universal set, and this slab is broken into pieces, and let us consider each piece is different subsets of the set X. Okay, and these pieces together form a base T1 of a topology T2. Okay, now we are breaking these pieces into more pieces like this. The new basis has many more pieces than the previous one, right? So if we call the new basis as B2, and this will form T2, this will generate the topology T2, then for every then B2 is the stronger one right here. T2 is the stronger one right here. B2 and T2 both are stronger than B1 and T1, since B1 has less element than B2. Since B1 has less element, so for any element, take this one, this is an element of B1, there always exists an element of B2 which is totally contained in B1. See, if we take a point, call it X, lying in here, for B1, take a close look. If you take X as a point lying in capital X, and this is the piece in B1 where this point lies in. Okay, this is the piece, this is a set in B1 where this point lies in, but there always exists a subset, this one, in B2, such that this subset contains this point, as well as this subset itself is contained in this bigger set. Okay, so this implies that B2 is stronger than B1.